This is a lecture from Open Tuition. To benefit from the lecture, you should download the free lecture notes from opentuition.com.
Right, well, let's carry on with the example we were doing, the linear programming example in chapter 6 of the lecture notes. And in the previous lecture, we'd formulated all the constraints, materials, labour, demand, and our objective to maximise the contribution. And I said the way we're going to solve it is to actually determine how many S and E we should make. We're going to use the graphical approach. So let me draw a graph and explain how we're going to do it. Now I don't have graph paper here, but I'll be as neat as I can. And remember, I said earlier, you can't actually be asked to draw one, but you can be tested on it. You could even give you a graph and check that you could interpret it. So make sure you do follow what I'm doing here. I'll draw a graph. So that was clever. Oh, that could do with being a bit neater. It's not perfect, but still. With two products, so I'll let that be S and that be E. Doesn't matter which way around they are. And before I explain how I'm going to use it, let me put scales on. I'll go up to 40 there, so that's about 20, 30, 10. It's not perfect, but still. If I go up to 40 here, 20, 10, 30. The way I'm going to use it, you see any point in that space will represent a certain number of S's, a certain number of E's. You know, that point there, for instance, it would represent 20 S's and 10 E's. And the first thing I'm going to do, because we've got those constraints, some combinations of S and E aren't possible. You know, we can't possibly make 40 E's, for example, because we're limited to 10. So the first thing we do is to actually draw the constraints on the graph. And let me show you how we do it. If I look at them in turn, first of all, materials. If you look back, I won't wind up and down, it's confusing, but if I look at the question, materials, it was 2S plus 4E was what we're using. And it had to be less than or equal to 80. Well, I'm going to put on the graph what happens when it's equal to 80. Well, you should know from school that any equation of that form, where you've no S squared, S cubed and things, is a straight line. 2 points fix a line. Any 2 points would do, but the easiest, if I look to see what happens when S equals 0, well, if S is 0, 4E is 80, therefore E would be 20. And for a second point, when E equals 0, if E equals 0, 2S is 80, or S is 40. So let me put those 2 points on the graph. S0, E20 is there. E0, S40 is there. And if I join them up, try and be neat. There's the graph of that equation, and it was materials, so I will label it materials. And the point is, before we look at the others, that any point on that graph, on that line, I beg your pardon, for instance, S20, E10 appears to be on the line, but any combination of S and E that are on the line, we'd be using exactly 80 kilos. Of course, there are lots of combinations of S and E on that line. However, the actual constraint was not that we had to use 80, but that was the maximum. We're going to use 80 or less. And so any answer we end up with, S and E either have to lie on the line and we're using exactly 80, or to be using less than 80, it'd be fewer S's or fewer E's, it'd be below the line. So whatever answer I end up with, S and E have to be on or below that line there. And we do the same for all the constraints. So there was the labour constraint, which was what? 5 hours, so 5S plus 6E. And again, we draw the graph of equality when it was equal to 180. And again, 2 points fix a line. When S equals 0, 6E is 180, so E equals 30. When E equals 0, 5S is 180, so S would be 36. So let's put those 2 points on the line. S0, E30 is there. E0, S36 is there. Join them up. Not perfect, but still. But there is our labour constraint. And in a similar way to materials, any answer we end up with, S and D will either have to lie on the line or be below it to be using less than 180. What else? Well, we've also got this demand constraint. S, remember, could be anything, but E was limited to 10. And so for E to be equal to 10, again, S anything, so it's this line here. That's it. No, it's not drawn. You probably can't see, but I'm trying to use a ruler. It's a bit tricky on this. But there's the demand. And yet again, you see, any answer we end up with must either be on that line, and E will be exactly 10, or it must be to the left of the line, because the requirement, E is either 10 or less than 10. The non-negativity constraints we don't need to draw. The axes themselves, we can't have minus E, we can't have minus S. Well, there are constraints, but what's important, of course, is that not only must we be on or below the materials line, but we've also got to be on or below the labour line. And we've also got to be on or to the left of the demand line, which limits us. For instance, you see, we can't have a point there, because although we're okay for labour, we're using less than the limit, we're using too much material and the demand's too high. We can't be here, because although the demand's okay, we're below the demand line. At that point there, we're using too much labour and too much material. And the only place we can be to satisfy all three of those constraints is the area which I'll label O, A, B, C, D. I'll go around it in red, then there's no argument. Do it without rubbing everything out. Ooh. No, not very neat, but still. Any answer we end up with must lie either inside or on the edge of that red area there, the red outline. If we leave the red outline, then we'll be breaking at least one of the constraints. And that area, you could test on the terminology, we call that area the feasible, which I can't spell out, stupid, feasible region or feasible area. So we have now limited the possible answers. But of course, there's still any number of combinations of S and D which fit on the edge of or within that area. We have to decide which gives biggest contribution. So let me go back to black. And what we do is this. Let me just clear some space, and I'm not going up and down too much. If you need to look back at that, you can always wind the video back. But what was our contribution? The contribution equation was C equals, it was 6 for an S, 9 for an E. But of course, I don't know what the final contribution is going to be. The answer might be $100, it might be $1,000. You know, that's what we've got to work out. But what we do, now be very patient with me here, and remember it's not going to be your problem actually doing this, but be very patient with me because I can't really explain what I'm doing till I've done it. You see what I mean? What we do, let me just invent a contribution. Again, I don't know what the answer will be, but just suppose the total contribution is 90. Now, for about the 5th time, I don't know what that's going to be the final answer. It may be 90, maybe 900. But just suppose for a minute I invented that figure. What would that mean? It would mean that 6s plus 9e was equal to 90. And let me draw it on the graph like I did the constraints. 2 points fix a line. So if s equals 0, e, 9e is 90, equals 10. If e equals 0, s, 90 over 6 would be 15. And if I were to put that on the graph, S0 E10 would be there, E0 S15 would be there. I'll join them. I'll use a dotted line, now we don't confuse it with the constraints. Now, anywhere on that line, any combination of S and E on that dotted line would give a contribution of 90. Now, why have I drawn that? Now, this is a bit to make sure you grasp. I don't know. I keep saying the same thing. I don't know it's going to be 90. Let me make up another figure. Just suppose it was actually, suppose it was 120. Six s plus 9e would be 120. Oh dear, not a bad day. 2 points fix a line. So if s is 0, e is, I could have chosen a nicer figure, couldn't I? 120 divided by 9, 13.33. If e equals 0, s equals 20. If I put that on, now I'm going to erase this after because otherwise it gets too messy, but S0 E13 is, about there. E0 S30, was it? S20, sorry, I'm stupid. Is there. And if I join those up, I haven't done them up very well. But the important thing is that those two lines would be parallel. I think you should know that what determines the angle of the line, whatever the value of C is, the angle is determined by the 6 and the 9. And so whatever C turns out to be, whether it's 90, whether it's 120, 200, 500, whatever it is, the angle of the line would be the same. The angle, the slope, the gradient there'd be a whole series of lines for different levels of contribution. But again, they'd all be parallel. And as you're about to see, all I need to finish this off is the angle of the line, the gradient. And so any contribution line would have done. I picked 90, fine. If instead I picked 120, it would be that second line. But it's only the angle, the slope, that's going to be relevant to me. Because what we say to finish it off is this. I want maximum contribution, whatever it is, S and E would lie on a line parallel to that one there. And also, as I hope you just saw, the bigger the contribution, although the line will be parallel, the bigger the contribution, the further away it would be from the origin. And so what we do, now it's very hard here to envisage it. I'm trying to think what way you can see. Ooh, you'll have to try and imagine. We take our ruler and we move it out on the graph, keeping it parallel. We move it further and further away from the origin. The further away we move it, the greater the contribution we're getting. But obviously there's a limit how far away we can go, because we can't leave the feasible area, the feasible region. And now again, I'm afraid it is rather tricky on this screen because you can't actually see my ruler. It might be an idea if you're at all confused to look at the answer. If I just sort of hold it up, we've got our objective function, we move it out as far as we can. And in fact, you'll find if you do move it out, you come to point C, you can keep going. The furthest point away is in fact point B. Now, I can prove to you later it is actually point B. But you see, it depends on the angle of the line. If the line was a very small angle, the furthest point away would be A. At our angle, it's B. If it was a bit steeper, it would be C. So potentially, it could be any of those corners. But the furthest point away would be one of the corners. And again, that's why I needed the contribution line. Keep it parallel. The furthest corner away is B. And just for the terminology, that was our objective line, or another name for it is the ISO contribution line. ISO meaning same, so anywhere along it is the same contribution. So I do now know that maximum contribution will occur at point B, but of course we do need to know how many units of S and D are. Is that? From the graph, bearing in mind mine's not perfectly accurate, it looks as though, it's about somewhere around 5 E's and 25, 26 S's. However, in the exam, although I've said you won't be doing the whole thing, what they're certainly likely to test you on is that you can determine the value not by reading from the graph, even if they've drawn you one, but you can determine it by solving the lines together. The point being that point B, where the maximum is where the labour line crosses the materials line. Remember, it could be any of the corners, but because of the angle of the contribution line, it happens here to be B, where labour crosses materials. Well, we know the equations for both lines. Two lines only cross at one point, and so you are expected to be able to solve them together algebraically. So again, let me clear some space. Maximum contribution occurs at point B. And as I just said, point B is where the labour line crosses materials line. So the labour line was 5S plus 6E equals 180. The materials line, 2S plus 4E equals 80. It's where those two lines cross, and so you've got to be able, to make sure you're able to solve two lines together. Simultaneous equations. Now this is something I think you should have done at school, and different people seem to learn it different ways, so it doesn't matter how you do it. I'll do it the way I learned at school and the way I prefer to do it, but there is only one answer. Do it any way you like if you've learned a different way. Just make sure, obviously, you can get the correct answer. But I'll show you what I do. Some people find it very odd, but as I say, it's your choice. Any way you want. What I'll do in this one is I'll take that second equation and I'll multiply it by 2.5. Now, I'll tell you why in a moment. But if I multiply each term by 2.5, 2 times 2.5 gives us 5s. 2.5 times 4 gives us 10e. And 2.5 times 80 gives us 200. Now the reason I chose to multiply by 2.5 is to deliberately have 5 s's in both the first and the third equation. And the reason I wanted that is if I now take away the first equation from the third, so we're in a sense upside down, but 5s minus 5s is 0, 10e minus 6e is 4e, 200 minus 180 is 20. And of course now everything's wonderful. If 4e equals 20, e equals 5. And now I know what the answer is for e. You can go back to either of the first two equations and work out s. If I go back to the first equation, 5s plus, well, 6e, 6 times 5 is 30, is equal to 180. 5s, subtracting 30 from both sides, is 150. S, therefore, is 30. Now, I know I keep repeating myself, but again, you should have learned how to solve the equations together at school. And it doesn't matter how you do it. I mean, there is only one answer that works, E5S30. So do it whatever way you like, as long as you get the right answer. If you can't remember the way you used to do it, then you do mine by all means. What I could have done instead, you see, I could have multiplied the second equation by 1.5, because that would have given me 6 e's in both equations. And again, we could have subtracted one from the other and got s, but it would have been the same answer. So there's how we're going to produce. It'll be 5 executive chairs, 30 standard chairs. The question also, though, said, what's the contribution that we'll get? Well, of course, that's easy. We've written down right from the very beginning, the contribution is 6s plus 9e. Well, we now know how many s's and e's. So 6 times 30 s's plus 9 times 5 e's. What's the total? 180, 45. There is the maximum contribution, 225. Just a couple of things before I leave this side of it, although there's a bit more to come. have a third lecture. Two things really. The first thing, less likely to be relevant in the exam, but although I draw my graph accurately enough, and the furthest point away was B, C is fairly close. You know, there is a danger of picking the wrong point. Well, B is in fact the best, but by all means work out the value at C, which is quick actually, because at C we know that E is 10, and it's where materials crosses E, so it wouldn't take a moment to work out. Wait, in fact, let's do it. Let's do it. I am in a sense wasting time. Sorry. I wouldn't have done this because I could see from my graph the answer's B. But at point C, E is equal to 10 because it's on the demand line. It was also on the materials line. C was where materials cross demand. And so the materials line, 2s plus 4e equals 80. If E's 10, then 2s plus 40 equals 80. 2s would be equal to 40, therefore s would be equal to 20. So those are the values at point C, but what would the contribution be? The contribution at that point would be, dear, it keeps doing that, 6 for each of 20 S's plus 9 contribution for each of 10 E's. 120, 90, it would be 210. It's lower. So that was a complete waste of time. But, you know, if you get muddled up over the lines, fine. It must be one of the corners. So whichever corner the line hits will give the highest contribution. If I wasn't sure and I checked point C, it does confirm it was point B that was the best. The other thing people often ask is, why do we bother drawing a graph? Why didn't I just solve for where all the lines cross? You know, it didn't take me a minute to, without drawing the graph, it didn't take me a minute to check demand against materials. We just did it. Earlier we did labour against materials, which is the one I know is right. It wouldn't take a second to check labour against the s-axis point A. Well, yes and no. You've got to be able to solve lines. But the trouble is, if you didn't have the graph, you'd solve where every two lines met. And the danger is you'd also end up checking that point there. Whereas what you can see from the graph, sorry, that's where demand crosses labour. You can see from the graph that that point there is in fact not possible because it breaks the materials constraint. So there is that danger. However, there we are. I'm sorry that's taken a while, but there is this problem that you've got to see the full solution, because any bit of that could be asked. You'd be asked to interpret a graph, you could be asked to write down the constraints, you could be asked, you could have been given all that and asked you to actually solve the lines together. All of it needs practicing. All right, well, there is the main solution. However, there is one more thing we're going to look at, but we'll have a break. I'll pause there, and then we'll carry on with exercises 2 and 3, which are based on the same example. So make sure you keep it in front of you. And as I say in the last lecture, I'll have the 2 extra bits on.